Welcome. After learning about the ways of cooling using the expansion valve and all this, we shall see some problems how to apply those theories. So, in this particular series of the tutorial, in this particular one, we shall be looking into the TS diagram, how to see TS diagram, then Carnot refrigerator, the minimum work done, and the ideal isobaric source of refrigeration using ideal gas. So, first we shall come to see that draw the schematic diagram of TS diagram and mark the constant pressure lines, constant density line and constant enthalpy lines. So, these are the ones which are the from the basis of the analysis, because every time you are going to analyze the problems, you have to see the TS diagram. So, first let us go to see that how we can read from the TS diagram. So, here I show that how this TS diagram is developed. First we draw this T axis and the S axis, that is the temperature and the entropy, and you will find these are given in the literature. You can find this will be given in some handbooks of, and you can maybe found in the reference books I have specified at the end of the lecture, or any other standard thermodynamic books. So, here we are saying how they look like. So, with this temperature axis and the entropy axis, and there can be various units of this temperature and the entropy. And first we will find there will be kind of dome. This dome represents the demarcation between the single phase and the two phase regions. On the left hand side of this particular thing is the subcooled liquid. In between we have the mixture of the vapor and liquid, and on the right hand side will be a superheated vapor, and this particular line is the saturated liquid line and this line is the saturated vapor line. So, this is how we represent this particular system on the TS diagram. Now, this particular point is the critical point. This critical point means above which we do not have any demarcation between the liquid and the vapor. Okay, and also we cannot liquefy a gas if we are above the critical point by lowering the temperature or increasing the pressure. So, we have to be below the critical point to make sure that we can make the phase changes. Now, here we find that we shall be having some lines which will be presenting constant pressure, and these are typical lines you will find on this TS diagram, which will be the constant pressure lines. So, you will find several such lines will be there on the TS diagram, and how will they differ? These pressures will be different, and we find this is a isobaric line with a pressure of P1, isobaric line pressure P2, and how the pressure are related? We find this pressure is more than this P2 is more than P1. That means, if we go from the right to left, we shall be going to a more and more pressure region, and then we shall be having constant density lines. And how they look? They are looking is similar to the constant pressure lines, only thing is that there is a kind of deflections are coming in this, and we find there will be several of these constant density lines, and we will find these will be having different densities, and these densities are related as the density as we move from the right to left, the density will be increasing. And next we shall be having the constant enthalpy lines or the isenthalpic lines, and in this we will find we had such kind of lines will be there on the system, and each of these lines will have the two different enthalpies, and this is enthalpy 1, enthalpy 2, and we will find that enthalpy 2 is more than enthalpy 1. That means, if we move vertically down, we will finding the enthalpy is decreasing. So, in case of pressure and the density, the value decreases as we move from right to left, whereas in case of the enthalpy, the value decreases if I move from top to bottom. So, this is how we find these things are arranged in a typical TS diagram. So, putting everything together, you will find that several lines will be there in the TS diagrams, and when we go for the solution of the problems, we will find the actual ones. Now, let us come to another problem. In this problem, we have given a Carnot refrigerator which is operating between 300 Kelvin and 72 Kelvin, and we have been asked to determine the coefficient of performance of the refrigerator. So, in this first we write the whatever information is given to us, and we put the proper symbol to them. The TH is equal to 300 K, that is the hot temperature and the cold temperature, and for this we are using this particular formula to find out the COP, and this is in this just we plug in the values of the various temperatures, so that we get the COP as this value. So, this represents by knowing the high temperature and low temperature, we can find out the COP of a Carnot refrigerator. And now next we come to another problem. In this we have to determine the work required to remove this about 200 watt of the power from a region from this 20.4 K, and we are given two different temperatures. So, if we want to remove the work to because we are trying to cool it down, so we have to take out the we have to do some work on the system. Okay. So, once is that this sink temperature, if it is 300 K, this is at 77 K. So, 300 K you can imagine as if we are throwing the work to the ambient, and this is some other liquid adjuvant temperature. So, we will find that depending on these two sink temperatures, our work requirement will also change. So, we just put all the input information here. So, we have to work with once with 300 K and then with 77 K, and this is the lower temperature available, and this is the work requirement. So, what we have to do that we write the COP value for the ideal system, and this is how we write the system, and we find that if we plug in the values of these various temperatures, we find this is the work requirement. So, we go for this is the work requirement if we are going for 300 K, and if we are going for 77 K, we find this is the work requirement. So, you can see easily that more the temperature of the sink, the more is the work requirement for a given Q. Okay, and for a given Q and for a given TC when TH is changing. So, we are going with the basic definition of the COP and to get the work requirement. Now, going to the next problem. So, here we are asked to find out the work again required for an ideal isobaric source, and earlier one was an isothermal source. With the isobaric source using the ideal gas as the working fluid that removes 2 kilowatt of energy from the low temperature source, and the temperature varies from 5 K to 20 K at the lower range. Okay, and the sink temperature is constant at 300 Kelvin. So, we put all the data given to us, and we have to find out the work. So, what we do that as we learnt earlier, this is the COP equation for the isobaric refrigerator, and here again this is the amount of heat that is to be removed, that is the work done, and here we found for the ideal gas, this is the expression we saw in our lecture, and we plug in the values these things, and we find that here we have the work done for the given value of the Q, and we plug in all the values here, we get the work done. So, here the sink temperature, and these are temperature within which the source temperature is varying. So, we find this is the work done, and negative sign shows that we are doing work on the system. So, this is a negative sign. Next problem, we have to find the ideal COP, that is the coefficient performance for again for isobaric source refrigerator, and which is operating reversibly between a sink temperature of 300 K and the minimum source temperature of 110 K and maximum is 180 K. And in this case, the working fluid is the gaseous nitrogen, whereas the pressure is the about 10 atmosphere. So, with this information, we have to find out that from the temperature entropy diagram, and please understand here we are not assuming any ideality. So, that is why we are not going to use the expression we have just used for the previous problem, which was in terms of only the temperatures. So, here in this case we have to use the actual TS diagram for the working fluid, and we are choosing in this case for the nitrogen. So, whenever you are solving this problem, but keep in mind that whether you are going to assume ideal gas or not, and depending on the condition given to you, you should be very careful in selecting that thing ideal or not. And in this particular problem, the pressure is high, the temperature is low. So, both these things are indicating that it will be wrong to assume an ideal gas. Okay, so that is why we have to go for the actual TS behavior. And it is very simple. You will see that only thing is that we have to locate from this thing. There are many isobaric lines here. So, we have to locate properly this. We have seen that it is 10 here. So, we are locating this particular isobaric line at 10 atmosphere, and whatever other things are done, we shall be just locating the various temperatures. So, T2 is 110 K. So, we are locating this value and we take a horizontal line over here, and this is the point of intersection of the isobaric line and the isothermal line, and at this point we have to read out whatever other things we need, whether it is density, whether it is enthalpy or the entropy. All these things we have to read out at this particular point, and to know these values we have to also do some kind of interpolation between the two values. So, we have to also know that interpolation techniques to get the values at this point of the various other thermodynamic properties. So, from this thing we are finding the H1 to be about this value, okay, and then we are taking the other, that is H1 S1 are here, which will be needed to find out the work done, and then we take another temperature T1. Again we are locating the isothermal thing, and we are finding the intersection at this point with this 10 atmosphere isobaric line, and again at this point we are reading the value of the S from this axis, whereas enthalpy is read from these isenthalpic lines. So, you will find that this particular point is not exactly falling on this isenthalpic line. So, what we need to do, we have to find interpolate the enthalpy at this point between these two enthalpies, okay, and then we are going for these values for enthalpy at point 2, and then what we do, that we are finding the COP, and this is the expression given for the COP for the actual gas, that the real gas, and again for the ideal thing, and we are just plugging the values of all these enthalpies and entropies which we have found out from the TS diagram, and we find that this is the value of the ideal COP. And if suppose somebody assumes that what would be the COP if somebody assumes nitrogen to be ideal at these conditions, that is what I was telling you, that be careful in choosing the or assuming the ideality. So, let us see if somebody does it, what happens. Now, if we again use this expression and we plug in the values only of the temperatures, and what we find, we get a value of 0.9. So, in this case we find that there is a slight difference between the two COPs. So, this shows that depending on the condition, the whether this application of the ideal or ideal real thing will be working out or not. So, if the COP of a Carnot is found out, we find that this is the Carnot COP. Okay. So, we are finding that the Carnot COP between this 300 K and 110 K, that is if we are assuming an isothermal source at 110 K. Okay. So, we are finding there is certainly a big difference between the values of the COP of the ideal COP or the Carnot COP depending on whether we have an isothermal source or a variable temperature isobaric source. And these are the various books which you can refer to for further details and explanations of these theories. Thank you.